Our speaker today is Efren Ruiz, and his title you can see there is the Algebraic Kirchberg-Phillips Question for Leavitt path algebras. Please, Efren, go ahead.
All right, thank you for the invitation. So today I would like to speak about the Algebraic Kirchberg-Phillips question for Leavitt path algebra. It's going to be somewhat of a revisionist kind of perspective where I tell you some of the things that's known, and then what's unfortunately a lot of unknown questions at the moment, so I just want to put everyone in line for those people who's somewhat interested in the problem, especially graduate students. What is the stumbling blocks and how to solve this question? So first of all, this is the terminology that was introduced by Cortines and Willie and Ruiz in their recent survey article about classification of Leavitt path algebra as this SPI graphs. So these are basically a graph that results in their Leavitt path algebra to be the simple and purely infinite algebras. And so that's the SPI for simple and purely infinite. So I thought it was a very clever choice of definition of a graph, and so I'm going to use it. So and so the algebraic Kirchberg-Phillips question essentially just says, is K-theory, or the pointed K-theory, a complete invariant for the Leavitt path algebras that are simple and purely infinite? And so for those people who's unfamiliar with K-theory, probably this group knows everything about it, but if you don't want to worry about that, then it's just really for these graphs, these are just the co-kernels of the 1 minus A sub E transpose, where A sub E is the adjacency matrix, which keeps track of the number of edges from V to W. And then the class of the unit will just be the ones where it's just the entries where it's all ones. So essentially, this is, I don't know how long now, maybe 15 or 20 years now in terms of the question, is if you have the K0 groups are isomorphic, which sends the class of the unit to the class of the unit. The question is, are the Leavitt path algebras are isomorphic? And again, this question arises as the algebraic model for where we have classification for graph C-star algebras, or in particular Cuntz-Splice algebras. And this is where the name comes from with Kirchberg-Phillips, because Kirchberg and Phillips prove for C-star algebras, simple, purely infinite C-star algebras, you have a complete classification. Okay, so the first thing I want to do is make a reduction to the question where it's just enough to prove that you have Morita equivalence between these two Leavitt path algebras, and this is due to Abrams, Lully, Pardo, and Smith in their Journal of Algebra paper in 2011. And I want to outline the proof because hopefully if I have enough time, I'm going to talk about the infinite graph case, and this comes into play in terms of the things that we don't know. So essentially, what we do is that given the fact that these Leavitt path algebras are Morita equivalent, then it's well known that it induces an isomorphism between the K0 group. Then we just compose that isomorphism, at least the inverse, with the chosen isomorphism that sends the class of the unit to the class of the unit. And essentially then the important piece here, then that means we have an automorphism on the K0 group, and this is where symbolic dynamics come into play. So Abrams and his co-authors uses a result of Wang that shows that any automorphism on this K0 group can be lifted to a flow equivalence. And this is where you get a Morita equivalence inducing the correct thing on K-theory. And then now what you get then after that is a Morita equivalence lifting this isomorphism beta. And then all of the algebraists will know that whenever you have a Morita equivalence for which the induced isomorphism in K-theory sends the class of the unit and the class of the unit, then these Leavitt path algebras are isomorphic just by going through the usual argument. And this is in blue is where I use this blue argument here. These are your standard isomorphisms. And then the isomorphism between the Morita equivalent sending the class of the unit to the class of the unit gives this isomorphism. So essentially then the question of the algebraic Kirchberg-Phillips question is just enough to really ask when are Leavitt path algebras Morita equivalent. And so so this is what I call the algebraic Kirchberg-Phillips Morita question. Is so I just removed the class of the unit and we asked whenever the K0 groups are isomorphic, then will the Leavitt path algebras be Morita equivalent? And I've already given you the argument of this direction. If we have the algebraic Kirchberg-Phillips Morita question, then you get the normal one with the unital version. And it's a result of Gene and Abrams and Num that you get the other direction as well. So, and the whole point is that if you have the isomorphism between the K0 groups are isomorphic, then essentially the class of the unit of the Leavitt path algebra in this direction here can be identified as a idempotent under this isomorphism to here. And then you just change the graph using corners of Leavitt path algebra is again another Leavitt path algebra. This is the result of Abrams and Num to get a honest to goodness pointed isomorphism between K0 groups. And by changing the graph, and of course their graph is actually Morita equivalent to the original one. So if you have the usual algebraic Kirchberg-Phillips with the unit taken into account, you'll have these two are now isomorphic, and then that's Morita equivalent. Oh, there's a typo here. This should have been an F there. Okay, so essentially what I'm trying to point out then for those people who haven't looked at this question is that if you want to solve the algebraic Kirchberg-Phillips question, it's really enough to solve this algebraic Kirchberg-Phillips Morita question where, is K0 a complete invariant up to Morita equivalence. Okay. So what is the current state of affairs for this question? Well, unfortunately, there hasn't been a lot of progress on it. I think it's a really hard question, but very interesting. And this is the most complete result, I believe. I should also say, Willie has done a lot of things about homotopy, up to homotopy. I'm not going to talk about that for today. I apologize, Willie, but I only have 50 minutes.
Good.
So the result here is that if you include the additional data of the determinant of 1 minus the adjacency matrix transpose as part of your invariant, then you do get Morita equivalent. Okay. And so the idea behind why this is true is that this determinant condition allows you to port results from symbolic dynamics. And so a lot of the classification results involving C-star algebras, this is where most of our ideas come from, is that we use a lot of symbolic dynamics, in particular flow equivalence, to tell us something about the graph C-star algebras. And so this is what Abrams and his co-authors did in this case as well. And so this is not quite how they proved this, And what I'm about to put as the idea of how the proof goes is not quite accurate, but it's really the general idea behind the proof. So what is the determinant condition gives us is that it gives us SL matrices over the integers. So determinant is equal to 1, and which somewhat conjugates one of the matrix to the other. Okay. And then we know from linear algebra, you know, U and V, since they're SL matrices, they can decompose as elementary matrices, as products of elementary matrix. And so you just have to be a little bit careful in how you decompose it. But the point then is that this allows us to do legal row and column operations, add additions and subtractions. And what I mean by legal is that, well, when I perform, for example, row subtraction or column subtraction, then I still stay within the class of SPI graphs, so simple purely infinite Leavitt path algebras, and these additions and row operations will still preserve the Morita equivalence. So this is sort of the recipe that my co-authors Soren Eilers, Gunnar Restorff, and Soren Eilers basically use to classify all graph C-star algebras. So once we get to these SL matrices, we perform these legal row and column operations. And then anytime if there's any questions, feel free to stop me. Okay. So the most outstanding question then in this business of trying to prove the algebraic Kirchberg question in the positive is this graph move called the Cuntz-Splice. Okay, so the Cuntz-Splice is taking a graph E and attaching this new graph onto it. And so the resulting here, when you do this Cuntz-Splice, is that it doesn't change the K0 group. And what it does is that it just changes the sign of the determinant. And that's important. The reason why is because when you have two Leavitt path algebras that have the same, that has isomorphic K0 groups, then their determinants of these kind of matrices only differ by a sign. And so this is a move that was introduced by Joachim Kuntz in the classification of Kuntz-Krieger algebras. And this is a way of altering the sign of the determinant without changing K-theory. So for graph C-star algebras, it's now known that when you do the Cuntz-Splice, you always get Morita equivalent graph C-star algebras, but this is the outstanding open question. And for Leavitt path algebras is, do we have always the Leavitt path algebra of E and its Cuntz-Splice? Are they Morita equivalent? And so this is the invariance of the Cuntz-Splice question as I have here. So my goal for a little while is to basically argue that the algebraic Kirchberg-Phillips question is equivalent to the invariance of the Cuntz-Splice question. So this is just giving you various ways of attacking this problem and see which way you want to go. Okay, so and so as I said, these are just the equivalent questions. And so here we have, if the invariance of the Cuntz-Splice question has a positive answer, then the algebraic Kirchberg-Phillips Morita question has also a positive answer. And again, I want to argue, I want to give us an outline of this proof because it I'll come back later again why I'm doing things that I will do later in the talk. Okay. So I again cite that if the determinant of 1 minus AE transpose and the same for F are the same, then we just invoke Abrams and his co-authors result to say, well, the Leavitt path algebras are Morita equivalent. So essentially, the Cuntz-Splice really will play a role when their determinant is different. And so, as I mentioned, the only time when you have isomorphic K0 groups, then the only difference between their determinants is that there's a sign change. So when they're not equal, then the determinant of one will just be minus the determinant of the other. And so what we do then, this is what we do is we do this double Cuntz-Splice. So basically, we take the graph E, you Cuntz-Splice it, and then you Cuntz-Splice it again. And since these are simple and purely infinite graphs, it doesn't really matter where you want to Cuntz-Splice any. You can just Cuntz-Splice another vertex. So all we're interested in is changing the sign of the determinant. So since the determinant of the Cuntz-Splice picks up a -1 from the original graph, when you do it twice, you don't change the determinant from the original graph. So you get the determinant there, and you have isomorphic K0 group, so you just invoke Abrams again. And then now, because the determinant of 1 minus AF transpose is the negative of the determinant of 1 minus AE transpose, then the determinant of the F graph and its Cuntz-Splice are going to be the same with the same K theory. So basically, then we're putting into business the Abrams machine to say that the Leavitt path algebra of E and its double Cuntz-Splice are going to be Morita equivalent, and then the Leavitt path algebra of F and the Cuntz-Splice of E will be Morita equivalent. And then where do we use the invariance of the Cuntz-Splice question is basically in the middle to relate the Cuntz-Splice of E with the double Cuntz-Splice of E. So this is Abrams here. This is Abrams and his co-authors here. And then in blue is invariance of the Cuntz-Splice question. So here I just argued that if we have the invariance of the Cuntz-Splice question, then we do have a positive answer to the Algebraic Kirchberg-Phillips Morita question. And really, the main argument that I want to point out here is that it's not just are the Leavitt path algebra of E and its Cuntz-Splice Morita equivalent. It's just really, if you take a graph E, you Cuntz-Splice it, then you double Cuntz-Splice it, are those Morita equivalent? And that's really the main point that I wanted to make here. All right. Okay, so basically this algebraic Kirchberg-Phillips question is a question with many faces. I think each of these questions are equally hard to answer, but really I think the main idea to prove is the invariance of the Cuntz-Splice question. This is probably the most doable one, and then you get the appropriate ones here as well, because these are all equivalent. All right. So what is the smallest unknown example about the invariance of the Cuntz-Splice? And so this is the famous L2 and L2 minus question. And I must admit, this is not my favorite presentation of the L2 graph, and we discussed it with Willie, but this is more towards, these are the classical representations of the O2 and the O2 minus graphs. So this is why I'm using it here. And so this is usually the L2 is usually the Leavitt path algebra of the graph with one vertex, two edges, and then you Cuntz-Splice that. But those are the same. They give the same type of algebras. And here, these are trivial K theory. This is why it's the smallest examples. And then there's determinants are different. It's 1 and -1 for the respective graphs. And so it's unknown whether these two Leavitt path algebras are Morita equivalent. And basically, majority of the questions of trying to answer the algebraic Kirchberg-Phillips question is trying to determine whether these two Leavitt path algebras are isomorphic. And this is sort of comes to my warning, because I think many, at least myself, I don't want to say everyone, I don't want to speak for everyone, but for myself, for a long time when reading papers here, I really thought that if you solve the L2 and L2 minus question in the positive, then you do get positive answer to the algebraic Kirchberg-Phillips question. That was my wrong preconceived notion so I was, as I was working through these things, I wanted to say, okay, yes, I just need to solve this L2 and L2 minus question, but it's unknown if this is sufficient in order to say the positive answer to the algebraic Kirchberg-Phillips question. Of course, if you prove that these are not Morita equivalent, then you'll get a negative answer for the algebraic Kirchberg-Phillips question. But it is, at the moment, for those people who haven't been looking at these questions, it is open that whether L2 and L2 minus are Morita equivalent, does that imply positive answers to the algebraic Kirchberg-Phillips question? And of course, then it's the same answer. Will that imply positive answers to the answer for the invariance of the Cuntz-Splice question? Okay, so this is me projecting onto everyone else that I made the error of thinking that that's sufficient, but then it's not
That's
known if it is.
That's a very common misunderstanding, yes.
Okay, thank you. So I'm not alone. Okay, so recently I posted a paper, and essentially what I was trying to do is find conditions for which you do get the invariance of the Cuntz-Splice question. And there is one already prior to this. It has to do with lifting a certain automorphism or isomorphism between L2 and L2 minus. That's due to Gene and his co-authors as well. But the recent result that I just posted is purely all about Leavitt path algebras. Certain Leavitt path algebras being isomorphic, then we get the invariance of the Cuntz-Splice. And so these are the two graphs, which I call F star and F star star. Now, these things didn't appear out of nowhere. These are graphs that we studied for invariance of the Cuntz-Splice question for graph C-star algebras. So this is just, all I did is took my paper with Soren Eilers, Gunnar Restorff, and Adam Sorensen on the graph C-star algebra, and realized that, oh yeah, we can do things in the Leavitt path algebra as well. So the result is, if you assume the Leavitt path algebras of these two graphs are isomorphic, then you do get the invariance of the Cuntz-Splice question that is have a positive answer. And then, of course, then as I outlined prior, is that then the algebraic Kirchberg-Phillips question has a positive answer as well. Okay, so this is what I call the cone L2 and L2 minus question. And the reason why I do that is because these graphs actually come from these relative cone path algebras, where the Kuntz-Krieger relation, CK relation, is imposed only on the vertex V2, and then the vertex V2, V3, and V4. So we don't put in the Kuntz-Krieger relations on these ones, the W1 and V1. And so that's why I chose the word here, the name for it. But these are exactly the L2 graph, and then it's Cuntz-Splice. All right, So I just want to give you a sense of how the proof goes and some comments about it after. So actually before the proof. So I just want to relate it back to the L2 and L2 minus question. So if you look at the Leavitt path algebra here, there is exactly one non-trivial ideal, which is corresponding to the sinks here. And its quotient is exactly the L2 graph and then the L2 minus graph. So because of that, then the assumption that the Leavitt path algebras are isomorphic, then you certainly get an isomorphism between the L2 and L2 minus. So the condition that I'm providing, which is the cone L2 and L2 minus question, if that has a positive answer, then it certainly implies the L2 and L2 minus question has a positive answer as well. Okay. So this is the unknown question if you want to try to solve that the L2 and L2 minus question is equivalent to the algebraic Kirchberg-Phillips question is if you do have an isomorphism between L2 and L2 minus, do you always have a lift between these Leavitt path algebras? And of course, if you do, then you'll get a positive answer to the cone L2 and L2 minus question, then you get a positive answer to the algebraic Kirchberg-Phillips question, and then so on and so on and so on. Okay, so this is just, this slide is relating the condition of having these are isomorphic and the L2 and L2 minus question. Okay, so I want to give you the idea of the proof because I think it has some nice ideas that can be generalized, I believe, and maybe loosen a little bit, which I thought about, but I don't have any formal things to say for today. And so I'm going to work with the cone path algebra, this relative cone path algebra, and I'm going to assume that they're isomorphic instead of the Leavitt path algebras. So essentially, as I mentioned prior, it's really enough to prove that these Leavitt path algebras of the Cuntz-Splice and its double Cuntz-Splice are Morita covariant. So in particular, we're going to actually prove that under this assumption, then they're going to be isomorphic. So what do we do is we use a result by Brownlow and Sorensen as we're just going to embed all of these Leavitt path algebras into L2. Okay, so the reason why we like this is because L2 has the property that every two non-zero idempotent are Murray-von Neumann equivalent. So this allows us to build a bunch of Leavitt E minus and E minus families in L2. Okay, and so I embed it here. That's the result that you can embed any countable Leavitt path algebra, countable graph, a Leavitt path algebra over a countable graph into L2. And then I embed this cone path algebra, which is also a Leavitt path algebra. And then I embed this one using the isomorphism here and that. And so I'll go into a little bit more details, but the upshot of what we do is then we use the isomorphism between these relative cone path algebras in and the embedding into L2 to build two families, one for the Cuntz-Splice of E and another one for the double Cuntz-Splice of E in L2, for which these families, these Leavitt E minus family and Leavitt E minus minus family generate the same algebra in L2. So once you get that, you get exactly these things are isomorphic because, well, the the Leavitt path algebra of the Cuntz-Splice is going to be isomorphic to its image of the Leavitt, the algebra generated by S, and then the double Cuntz-Splice Leavitt path algebra will be isomorphic to its image with the algebra generated by T. And then because by construction, the algebras of S and T are going to be the same in L2, you get isomorphism. Okay. So the question is really, how do we use this isomorphism to build S and T? And I just want to show you by an example where this isomorphism plays a role. And now in particular, this double Cuntz-Splice will be a very specific vertex that I'm Cuntz-splicing after I Cuntz-splice again. Okay. All right, so here is my original graph. So this, and then I Cuntz-spliced it here. And now the double Cuntz-splice, I don't want to just randomly choose where I'm going to Cuntz-splice it. I want to Cuntz-splice this graph at exactly V1. So this is basically now the double Cuntz-splice. So I don't Cuntz-splice at U again, where I did here. And the reason why I want to do that is because now notice in blue, this is exactly these, the graph for L2 and the L2 minus graph. So now you have to imagine that we're all of these things are living in L2. So I do this embedding. And so then now how do I choose my Leavitt E family for each of these graphs? Well, I just follow the nose, my nose here. The Leavitt E family for this graph is, well, I'm going to choose these edges and this vertex. And I'm going to choose these edges for this and these vertices as well. Now I have to do something with what's attaching, and that's why I have it as a dotted line. And then I'm going to do the same here. So I use these edges and this vertex, and then I use everything in blue. And so the adjustment really is coming from how we attach it to the original graph here. And so this is where now we're living in L2, where I made the comment that given any two non-zero idempotents, they're Murray-von Neumann equivalent. And this is where we use the fact that we can find a D1 and D2 that makes, we get the Kuntz-Krieger relation holding at V1 and U. So we just do that. And remember, in the cone path algebra here, the Kuntz-Krieger relation is not imposed here. So when you look at V1 minus E1, E1 star, minus E2, E2 star, that is a non-zero idempotent. So basically, that's how we now take that non-zero idempotent and Murray-von Neumann equivalent to U. And so this is sort of how we get our D2. And then we do the same for D1. So at the moment, it's important is that this isomorphism is not used to get this D1 and D2 here for this graph. So what do we do now is this is where this isomorphism plays a role. And in particular, this isomorphism gives us certain idempotents in these cone path algebras to be equivalent. And this is where we use that equivalencies to get these ones here so that we get the right Kuntz-Krieger relation there. And they're going to be generating the same because remember, this cone path algebra and this cone path algebra is assumed to be the same. So these generators are going to be living in the same thing. These are the same generators. And because of this isomorphism, we can choose D1 and D2 to be living in the same algebra as well. So this is where we use the isomorphism here.
So sorry, are the D1 and D2 in the second graph the same elements as those in the first? What are
So
they?
V1 and V2 here, and then these ones?
Yeah, the D's there, are they D primes or are they the same D's? I mean, because you are living.
They're the same V's.
Okay.
Yeah, yeah. So these are the same V's here from these ones, and this is the same W's for that one. So now basically what I'm doing is that I'm identifying all of these in L2, and they're equal now. They're the same in L2 when I did this embedding. So when I take these generators and these generators in the L2, they're generating the same algebra because they come from this isomorphism and then embedding it to L2. Does that make sense?
I still have to think about it. But I mean, I still don't see why, D1 in one of the two directions, D1, D2, or D2, D1, one of them gives W1. And in the opposite direction gives you U. And but is W1 the same as V1?
Oh, no, not necessarily. You don't, because yeah, so W1, you're saying in this isomorphism is V1 the same as W1?
Yeah,
is that correct?
If not, yeah, but the reason I'm asking that is if it isn't, then why would D1 go to D1 and D2 to D2?
Wait, what do you mean V1 going to V1?
Well, after you apply your isomorphism and your embedding, you are living inside L2.
Yes, that's
Now,
correct.
inside
Yes.
L2, the D1 and the D2 on the first graph
Yeah.
are the same elements as the D1 and the D2 and the second.
Oh, but the second graph is not V1 and V2. This is W1, W2,
No,
W3.
D, as in
oh, yeah. Okay, so I was supposed to put a prime here.
Yeah, that was my
okay. Yeah. Thank you. So I was supposed to put a prime here because it's not this D1, D2. I apologize for that. I was supposed to put that. So what we do is that the whole point is that once we've constructed D1 and D2 here on this graph, then we use this isomorphism to adjust D1 and D2 to get a D prime and D2 prime to get this Cuntz-Krieger relation for this graph. And the adjustment of D1 prime and D2 prime still stays in the same algebra that it generates in L2. Yeah, so I apologize. It's supposed to be different. It's not meant to be the same.
Okay,
copy paste error. Yeah. Okay. So that's the idea of the proof, and then we get this result. And if you notice, then I specifically chose how to double Cuntz-Splice, not random, but it was actually, Cuntz-splicing the Cuntz-Splice graph. So that was important in this way of proving it. Okay, so basically, as summarizing here is that if you want to try to prove that the algebraic Kirchberg-Phillips question is positive, then you just prove the cone L2 and L2 minus question is positive. But if you want to prove it as negative, then you want to prove that the L2 and L2 minus question is negative. So this is sort of your strategy now. For me personally, I actually would want a negative answer, but because it ties into more flow equivalence, because I'm much more liking symbolic dynamics at the moment, but that's my personal preference. But I would like just an answer to it, positive or not. Okay, So with the time that I have left with the 9 minutes, I just want to briefly go over what happens beyond the finite graph case, because it has a very interesting contrast, because some of the things we have automatic, well, not automatic, but we have that's different from the finite case. Okay, so I'm going to talk about only vertex finite, so finitely many vertices, and countably many infinite edges. Okay, so this is an example. And so a result of myself with Mark is that we always have, in this scenario, the invariance of the Cuntz-Splice question. So the Leavitt path algebra of E and its Cuntz-Splice is always Morita equivalent. So we always have this now. So you might say, well, this is good. That means for countably infinite graph, we have always the Algebraic Kirchberg-Phillips question. But there's an issue here, which I will get to. And another thing that we prove is that we can determine exactly when two Leavitt path algebras over these countably infinite graphs are Morita equivalent. That's when their K-theory, K0 groups are the same, and you have to always take into account the number of singular vertices. This comes out. Now, you might say that this is not as nice because this is not K-theoretic, and the good thing is that Willie and Montero also has a result here that allows us to have a K-theory invariant. So the KH0 is the, oh no, I'm blanking. It's the homotopy K-theory. And then the KH1 is with this algebraic KK theory that we have. And the whole point is that with these information, you can read off the number of singular vertices. So putting together my result with Mark, with Cortinas and Montero, you get exactly classification using K-theoretical invariant as well.
One small point I want to make is that if little L is a field, then the KH0 and K0 are the same. So it's only the only difference is you replace singular vertices by KH upper one.
Yeah. Thank you. Okay, and so I just sort of want to briefly go through as an example, because this is really why we get Morita equivalence with O infinity in the Cuntz-Splice. And it's really the general idea of the proof is that it's just a bunch of moves that induces Morita equivalence. So we take O infinity or L infinity, sorry, and then you outsplit where you take one of the loops and put it on its own partition. And then we outsplit again. We just take one of this loop here and put it in its own partition. You have that graph. And then you take this edge F and you outsplit that with that own partition. All of these O's preserves Morita equivalence. In fact, they're isomorphic. And the key now is that this is a vertex that does not support a loop, a cycle of length 1, so we can collapse it. So that means we're going to get a loop on this vertex here. And so when you collapse it, you get that graph. And this is where I'm also using, what's important is that I'm using countably infinite graphs, is because countably infinite union countably infinite, you get countably infinite. So I don't know what happens when you deal with uncountable edges. I actually have some students working on it, but I think it's a hard question. So now what I'm going to do is show you that when I Cuntz-Splice the O infinity, I can get to this graph. So I start with the Cuntz-Splice. I do an O where I have F on its own partition and E and G in the other partition. So I get this. And then you get another vertex that doesn't have a loop on it, so we collapse. And then there's a concept of move T that we can apply to just put infinitely many edges up on both this one and that one, because this vertex has infinitely many edges coming here. And that's basically the graph that we came up with with O infinity. And then you can do this matrix representation as well. And this is really the idea of Adam Sorensen for graph C-star algebras. And he does these Frank's moves for matrices. And you can do that for these infinite graphs. So the question then is really what happens in the unital case. So if you add the class of the unit, then are the Leavitt path algebras isomorphic? And the smallest example that is not known is really these two Leavitt path algebras of these two graphs. So this is the L infinity graph. And this one is very simple-minded because if I remove this source, you get Morita equivalent of the O infinity graph, because that's just the outsplitting. So these two graphs are Morita equivalent, but we don't know if these are isomorphic or not. And this question is equivalent to the existence of a Morita equivalence between self-equivalence of L infinity that induces the non-trivial automorphism on the K0 group. So I don't know if there is such a non-trivial automorphism. If you've seen Soren Eiler's talk, he's been talking about these graphs, at least for the graph C-star algebras, for a while now. And the question is, do we have a diagonal preserving isomorphism between the graph C-star algebras? These are all open questions that we don't know at the moment. And this is the reason why for Leavitt path algebras, all of our technology that we have always preserves the diagonal. And so that's why, because we don't know if we have an isomorphism preserving the diagonal, we don't know we have an isomorphism between these Leavitt path algebras. So I'm almost done with my last slide. I just want to summarize basically what we know and what we don't know in both the finite and the infinite case. So the finite, we can lift any automorphism of the K0 group. This is really a result of Wang, and then everything else we don't know. Invariance of the Cuntz-Splice and these algebraic Kirchberg-Phillips question. For the infinite case, we do know we always have the invariance of the Cuntz-Splice. We do have the algebraic Kirchberg-Phillips Morita question, but we don't have the unital version of these things in general because we don't know if we can lift every automorphism of the K0 group to an automorphism or at least a Morita equivalent of the Leavitt path algebras in the infinite case. So I will stop there and thank you for listening.
Okay, thank you, Efren, very much for a very nice talk. Are there questions from the audience? See anyone? Otherwise, I didn't understand what the move T was.
Okay, yeah. Let me go back to the move T here. So this is a move that we when we studied these amplified graph C-star algebras, when we invented. And so the idea is that if you have infinitely many edges from one vertex to this one, so like this one right here, then anything that this vertex point to, you can just put infinitely many edges as well. So here you have this vertex that has infinitely many edges. that goes to itself. And so anything that it points to, you can just replace it with infinitely many edges. And so that's why I have infinitely many edges here and infinitely many here. So that's sort of the idea behind it. And if you're wondering how you do that in terms of the normal moves that we have for Leavitt path algebras, what would you do is that you would outsplit this with this edge that comes out of to that vertex. And then now it's gonna not support a loop, so you collapse it. And then when you collapse it, you'll get infinitely many edges. So that's how this move T occurs.
Okay, there is a question in the chat by GeNoCAS. He asks whether you have a conjecture about what the answer to the algebraic KP question is.
I wouldn't say I have a conjecture, but I have a wish. And my wish is that it's no. I would like to have the Algebraic Kirchberg-Phillips question to be in the negative. And the reason why I would like that to have it is because then there's a distinction between Leavitt path algebras and graph C-star algebras, where the Leavitt path algebra now reads off the sign of the determinant, hence flow equivalence. And that's my preference.
I see. Yeah, but couldn't it be that, so if,
I guess,
is it true that if for some SPI graph, finite SPI graph E, the Leavitt path algebra of E and the Leavitt path algebra of its Cuntz-Splice is isomorphic, then would that force the same be true for every graph E? I don't think so, right? I mean,
so you're saying if you have a graph E for which the Leavitt path algebra of the graph E and its Cuntz-Splice are isomorphic, then you have the invariance of the Cuntz-Splice question is true.
Yeah, I'm asking
for any graph,
because it could be if the answer to this is no, then it would give. So I mean, if you have a negative answer to give a negative answer to the KP question, is to say that there exists a graph E such that that the Leavitt path algebra of E and of E minus are not isomorphic. But then that doesn't mean that it's not, that doesn't completely solve the question of what you need to classify them.
Right. But there are graphs for which the graph E and its Cuntz-Splice are isomorphic, but we don't know in general that they, you get the result in general, because you just take any graph with 1 minus AE transpose have 0 determinant, then
Yeah, of course.
Yeah. So if you're trying to answer those kind of questions, you would want graphs with non-zero determinants, because that's where the
finite K0 groups.
Yes, that's correct.
Okay, are there any more questions from the audience? So if not, I will stop the recording now.